In the second part of this lecture, we move to discuss the concept of power and maximum power transfer. When you have a voltage applied across a resistor, then the power delivered to that resistor is equal to V equal to IR, or I squared R, or V squared over R. These three expressions are identical. For DC, when the voltage is DC, when the current is DC, means they do not change with time. This power is really the expression for the power, and it is the instantaneous power, and it is the average power, because the power is constant, does not change with time. But when we talk about time varying quantities, as I'll be showing you very soon, the power B of t is really the product of V and I becomes what we call the instantaneous power. So when you multiply the voltage across a resistor by the current going through that resistor, you are getting really an instantaneous power. The average power, you have to integrate this instantaneous power over time. Of course, this power is lost in the resistor in the form of heat, and this heat is really a result from these electrons flowing through this type of resistor, and then making collisions with the atoms of the resistor, so they start to heat, and then you get this resistors heating, and then you get this thermal power dissipated. Usually for commercial grade resistors, you mention, in addition to its value, the power dissipation or maximum power dissipation. So there are resistors that can stand few watts, some that can few hundreds of watts, and so on. A very important problem that we see very often is how to maximize power being transferred to a load. So here in this case we have a load RL, and it's connected to a Thevenin equivalent of a circuit. It has a voltage equivalent V Thevenin, an equivalent resistor R Thevenin. So our target here is to determine what is the maximum RL, or what's RL that will result in maximum power transfer from the voltage source to the resistor. Of course, if you increase the value of the resistor, then you are decreasing the current. Then I squared R, the product of I squared R, you have I going down while R is increasing. So you have here some sort of two opposite conditions, and in that case there is an optimal value. This optimal value is a very well known result that we know in electrical engineering. I thought it's very important to show you this derivation, so let's go over that. The voltage across this resistor is simply obtained by voltage division. So there's a voltage divider, so it's V Thevenin multiplied by RL over RL plus R Thevenin. This is VL. This is the voltage across this resistor. Now, the power dissipated in the resistor is simply V squared over RL. So it is this voltage divider expression or the VL expression that we derive together, multiplied by 1 over RL. Now RL will cancel with RL squared, you end up with RL in the numerator. Now our target is to maximize this power. This is a power delivered to the load resistor, and our target is to determine RL that will make this maximum. Notice that RL appears in the numerator and in the denominator. This means there is an optimal value for RL at which the power reaches its peak. And the way we do it is that we differentiate the power, and then relative to the resistance, and then we set this first order derivative to 0. So this gives us all the critical points at which the derivative vanishes. So if you do that, you get here you square the denominator, so this becomes power 4, and then the denominator multiplied by the derivative of the numerator, so RL will give you a derivative of 1. V Thevenin squared stays outside, it's a common term, and then minus the numerator, so minus RL multiplied by the derivative of the denominator relative to RL. So this gives you 2 R Thevenin plus RL. So you end up with minus 2 RL, R Thevenin plus RL. For this term to vanish, the numerator has to vanish. And when you combine the terms in the denominator and you expand them, you expand this one into R Thevenin squared, 2 R Thevenin RL plus RL squared. You notice that RL squared, 2 R Thevenin RL will cancel with 2 R Thevenin RL, and then you will see that you end up with this term here. And for this term to be 0, R load must be equal to R Thevenin. So this is a general finding that we use in electrical engineering. For DC circuits, in order to have maximum power delivered from a voltage source to a load, the value of that load must be equal to the value of the resistance, the internal resistance of that voltage load. Here we call it R7. So in a configuration like this one, to have maximum power transferred from the voltage source to RL, RL must be equal to R7. And in that case, only 1/2 of the Thevenin voltage will appear across the load resistor, because this now becomes a voltage divider with a value of 1/2. Half Thevenin voltage here and half Thevenin voltage on the load resistor. Now let's take a look at an example. We have here a circuit. This circuit has two voltage sources, 200 volts here, 160 volts here, and then you have 6K and 4K. Our target is to determine the value of RL, this load resistor, that will result in maximum power transfer from the circuit to this load, from the circuit to this load resistor. So the way that we do it is that we try to find the Thevenin equivalent seen between these two nodes here, between this node and this node. Okay, so we determine the Thevenin voltage, the Thevenin resistor, and then we set RL to be equal to the Thevenin resistor. In that case, we guarantee maximum power transfer. How do we find the Thevenin equivalent? Well, we have to first find the Thevenin voltage, which is obtained by creating an open circuit between these 2 points. And then we find the Thevenin resistor by removing all the sources and then trying to find the open circuit resistor seen between these 2 points after RL is removed. So we follow these 2 steps, determine the Thevenin equivalent circuit, and then the maximum power transfer will happen when RL is equal to R Thevenin. So first, to calculate the Thevenin voltage, we created an open circuit here. When we did that, we would like to determine V Thevenin. So this voltage here, this is positive, negative. So this is just one loop. You have one current flowing in this direction because this one has a higher potential than this one. So the current flowing is simply equal to 200 volts minus 160 volts divided by 6K plus 4K. It's just simply one loop with 2 voltage sources and 2 resistances. So this results in 40 divided by 10K, or 4 multiplied by 10 to the minus 3, so it's 4 milliamperes. So the current I in this loop is 4 milliamperes. Then V Thevenin, which is the voltage seen between these 2 points, as shown here with this polarity, is simply equal to 200 volts minus 6K multiplied by I. So if I remove the voltage drop across this resistor here, if I remove this voltage drop, so this, what remains will be equal to V Thevenin. So V Thevenin is equal to 200 minus I, which is 4 milliampere multiplied by 6K. So when you do that, it becomes 200 minus 24 volts. So the V Thevenin here in this case 176 volts. Now the next step is to find the Thevenin resistor, or Thevenin resistance, and the way we do it, we remove these sources, we make them all short circuit, and then to try to find the input resistance seen between these 2 terminals. So after you eliminate the voltage sources, the circuit becomes very simple. You have 4K in this branch, 6K in this branch. So looking into this circuit, you see 6K in parallel with 4K. So it's 6 multiplied by 4 over 6 plus 4. And I take into account that this 10 to the power 3, but I write K later. So this will give you here 24 divided by 10. So it gives you 2.4 kilo ohm. This is 2.4 kilo ohm. So for maximum power transfer, the load resistance RL must be equal to 2.4 kilo ohm. And in that case, only 1/2 of the Thevenin voltage will appear across the resistance. And I can get the expression of the power. It's simply equal to the square of the load voltage divided by RL, where this load voltage is half the Thevenin voltage. So the expression for maximum power transfer is VL squared over RL, where RL is equal to V Thevenin and VL is equal to half, when RL is equal to R Thevenin and VL is equal to 1/2 of V Thevenin. V Thevenin is 176 volts, so with that, R Thevenin is equal to 2.4 K, so 2400 ohms. If you divide these two together, you end up by 3.23 watts. So the maximum power that can be transferred from this circuit to the load resistance happens when the load resistance is equal to R Thevenin 2.4K, and in that case the value of this maximum power delivered is 3.23 watts. We talked so far about resistances, but now we'll start to move to talk about other components in electric circuits, the inductors and the capacitor. These are the two or the three most widely used components. For resistances, we have seen it before. V is equal to IR. The instantaneous voltage follows the instantaneous current, or the current is equal to V over R, and it does not have a memory. It does not have a memory, meaning that the current does not depend on past values of the voltage. The current does not depend on past values of the voltage. While for capacitor, things are a little bit different. Because a capacitor is really an element that stores charge. And the stored charge in the capacitor is linearly proportional to the voltage. This is the case for a linear capacitor. So Q is equal to CV. V is the voltage across the capacitor, and the Q is the charge across the capacitor, or charge stored in the capacitor. Notice the polarity here. If this is the positive to the negative terminal, then there will be a positive charge accumulated on this plate, negative charge accumulated on this plate, and the current is flowing from the positive plate to the negative plate. The current in any device, and in that case in the capacitor, is equal to dq by dt. The current is always the rate of change of the charge. But Q is equal to CV, and C is a constant. Then I can take C out, and I becomes equal to C dV by dt. So for the capacitor, the current is really proportional to the derivative of the voltage, which if I integrate both sides, divide by C and then integrate, the voltage is the integral of the current divided by C. You integrate from minus infinity to t. So this device is said to have a memory. Why it has a memory? Because the voltage at time t depends on the current at all previous values from minus infinity to t. This is why we call it a memory or a device with a memory. Remember the integral from minus infinity to t of I. This will give you the charge. So this is the charge at time t. So this expression is really nothing but V of t is equal to Q of t over C. So keep in mind that the relationship between the capacitance, the charge, and the voltage in the capacitor is Q equal to CV, or Q of t is equal to CV of t, when everything is changing with time. The same thing happens for inductors. In inductors, we call an inductor a linear inductor when the flux, magnetic flux created by that inductor is linearly proportional to the current. So the more currents flowing through this coil or through this inductor, the more flux is being generated. This magnetic flux, magnetic energy. So phi is equal to Li. But it's known from Faraday's law that the voltage across the inductor is equal to d phi by dt. The rate of change of the flux gives rate to voltage. So if I replace phi here by Li, but L is a constant, I can take it out. We know that in the case of the inductor, the voltage is linearly proportional to the derivative of the current, or the current is linearly proportional to the integral of the voltage. So here we say that this device has a memory. Why? Because the current at any time t will depend on all previous values of the voltage. It's the integral of minus infinity to t v of tau d tau. Integration means memory. And then you divide by L. Remember that the voltage is the derivative of phi, then phi is the integral of v. So this expression is nothing but v of t. So for an inductor, for a linear inductor, phi is equal to Li. I should mention that for the case of nonlinear capacitor, nonlinear inductor, the capacitance can be a nonlinear function of the voltage, or the flux can be a nonlinear function of the current, which is a little bit an advanced case, which I'm not going to be discussing in this course. Now let's take at an example, and I will be focusing in my examples on capacitors because this is what we're going to be seeing very often in this course. Most of the elements used in biasing transistors and then coupling them are capacitors. So this is why I'll focus more on capacitors in my examples. Consider here a voltage pulse given by 0 if time less than or equal to 0. It's equal to 2t volts if t between 0 and 2. Is equal to 4 e to the minus t minus 2 volts for t is greater than or equal to 2. And this voltage is applied to the capacitor. Capacitor is 10 microfarad. We would like to determine we would like to sketch the capacitor voltage and current. This is the capacitor voltage, but what we have to calculate, we have to calculate the capacitor current. Of course, we have to go back to the expression relating the current and the voltage of the capacitor, which is I equal to C dV by dt. So the current is proportional to the rate of change of the voltage or the derivative of the voltage. So we have to determine the derivative of the voltage in all the three expressions, and then this will determine for us the value of the current. So here we say that I is equal to C dV by dt. For the first part, when there is no current in this part, when t is less than or equal to 0, there is no current, then the rate of change of the voltage is 0. V is equal to 0 here, then rate of change of the voltage is 0, then the current is 0. So in this part the current is 0. Don't have to worry about here. For this part, the current is linear. For between 0 and 2 seconds, the current is linear. It's equal to 2t, but I keep on saying the current. It's actually the voltage that's linear. The voltage goes from 0 up to 4 volts in 2 seconds. So the voltage is a linear function of time. So in that case, we say that the current is C dV by dt. The derivative of the voltage here is simply the slope of this line, which is equal to 2. So in that case, the current in this part here will be a constant, and it's equal to the capacitance, which is 10 microfarads. So 10 multiplied by 10 to the minus 6 multiplied by the slope, and the slope is 2. And this comes from this expression here. So the current in this part will be constant, equal to 20 microampere. Now we would like to determine the current in this part. Again, this is an exponential term. We have to differentiate it relative to time to find dV by dt, and then multiply it by the capacitance to find the value of the current. And the current in this case as well will be a time varying quantity. So for time t greater than or equal to 2, you see that I is equal to C dV by dt. C is equal to 10 to the minus 6. It's 10 microfarad. If you differentiate the voltage that we have, which is 4 e to the minus t minus 2, the exponential term will give you only here a negative sign. So this is the derivative. If you multiply minus 4 by 10, you get minus 40 e to the minus t minus 2 microampere. So when t is equal to 2, the current starts with minus 40 microampere as shown here, and then it starts to decay gradually and slowly to 0. Notice something very interesting about capacitors. In a capacitor, the current can suddenly change from a positive current 20 microampere to a negative current which is minus 40 microampere. But the voltage does not change instantaneously. The voltage has to change in a smooth way. Okay? So the voltage in a capacitor has to be a continuous function of time. The reason for that is the fact that I is equal to C dV by dt. If the voltage changes suddenly, then the derivative of V relative to time will be infinite, which means that it will result in an infinite current. But infinite current is not possible, because infinite current means that you have an infinite flow of charges. So because the current has always to be finite, the rate of the voltage has to be continuous with time. It does not have to be differentiable, it has to be continuous. Okay, so this derivative here cannot. It has to be a continuous function of time. It does not change suddenly, otherwise result in an infinite derivative. Infinite derivative here means infinite current, which is not the case. Anyway, this is an advanced question I just want to mention to you. So in a capacitor, the voltage has to be changing smoothly with time, while the current can undergo a sudden change, as we've seen here. It can go suddenly from 20 microampere to minus 40 microampere in 0 time. Of course, in reality, there may be some slope, but nevertheless a very sharp change. Now, I will end this lecture by discussing how a capacitor is charged and discharged through a resistor. The first scenario that we have a battery. It is charging a capacitor, okay, through a resistor R. So here there will be a current flowing in this loop, okay, and this current will accumulate positive charges on this plate and negative charge on that plate. We write the differential equation governing this circuit, and then we try to solve it. The equation that we have is that the voltage, this battery voltage, is equal to the capacitor voltage plus IR, the drop across this resistor. But the capacitor voltage is nothing but Q over C. We have agreed that for a capacitor, the charge and the capacitor and the voltage are related through the capacitance. So V is equal to Q over C. Now I can replace I, the current flowing in this circuit, by dQ by dt, where Q here is the charge going through the capacitor, and then I can remove this term to the other side and then multiply, and then what I'm going to be doing here is simply divide both sides by R. So I replace I by dQ by dt, and then I divide both sides by R, and then I remove this Q over C to the other side. So this is a differential equation you end up with, okay? And if I organize things a little bit, I can make RC a common denominator. This gets multiplied by C, this one will remain the same. So we end up by this differential equation here, which I will write for you on a separate line, just to make it clear that dQ by dt is equal to CE minus Q over RC. This is the equation really that we have. This is the first order differential equation. We can integrate it very easily. We can divide this side by CE minus Q, and then integrate the other side relative to T. So this is what we did here. We'll assume that the capacitor will start charging at time 0, and then it will go up charging up to time T. And during that time, the charge will go from a charge 0 to charge Q. Notice that in this expression, as assume that the charge is equal to 0. But I could have assumed some initial charge Q naught. The only difference that this will make is that in this part here, maybe I can draw it for you here in this term here, you will have another Q naught. Okay? So I would like you to verify this, and this will result in a little bit different expression at the end. So for this expression, I'm assuming that the capacitor charge with start with zero charge, and then it goes charging for time T, and during that time the accumulated charge will go from 0 up to Q. Of course, the integration of this term relative to Q will give us a ln. You put the upper limit, you get Q. You put the lower limit, you get 0. Of course, if the initial charge is not 0, you get here Q naught. And you integrate dt, you get T. Put upper limit, you get T. Get lower limit, you get 0. You get this expression. I can simply raise both sides to E exponential of E, and then multiply both sides by E. I end up with this expression. This expression is simply saying that Q is equal to CE multiplied by this exponential term, or if I divide both sides by C, Q over C is the voltage. This expression is simply saying that the voltage at any time T is equal to the battery voltage multiplied by 1 e to the minus T over RC. So this means that at time T equal to 0, there is no voltage across the capacitor. This term 1 minus 1 will give you 0. But as time goes to infinity, this term will approach 0, and then the capacitor will be fully charged to the battery voltage. Okay? And this expression actually will change a little bit if you have some initial voltage, and I will leave it for you to do that. Start here by having this Q naught. If there is an initial voltage on the capacitor, it did not charge from 0, then the expression that you will get is that V is equal to E plus V naught minus E to the minus T over RC. I would like you to verify this expression for yourselves. It's not that difficult to know. E is the battery voltage, and V naught is the initial voltage on the capacitor when it started charging. The term RC is very important for capacitors, and you will have to remember this one. This is the capacitor time constant. It really determines how fast this capacitor is charging or discharging. I now know the expression for the voltage from this one here. If I want to get the current, it's not a problem. I have all the expression for the charge. I can differentiate the charge expression relative to time to get the current. If you differentiate this one will give you a negative sign. And then you have, of course, you have this one here. So you get also 1 over RC when you make the derivative. C will cancel with C. You end up here with E over R. So this will tell you that at time T equal to 0, you have an initial current, high current, E over R, flowing in the circuit. So this is the initial capacitor voltage, initial capacitor current. But as time goes to infinity, this term goes to 0, and then there will be no current charge flowing in the circuit, which makes sense, because in that case the capacitor will have fully charged to the battery voltage. See, here you have E, and here you have E, and there is no current in the circuit at infinity. Okay, so remember, I naught is the initial current, it's E over R, and we will know that if you allow time to go by 1 tau, tau here is a time constant, if you allow it to go by 1 tau, you will see that the capacitor current will drop to only almost 1/3 of its initial value. It's always decaying with time, it goes to 0 in infinity, and this happens while the capacitor is fully charged to the maximum voltage, which is E. We can derive exactly the same expression for a capacitor discharging. So here we have a capacitor, it's charged to some initial voltage, and then you connect it to a resistor, then the capacitor will start discharge. Remember, current will be flowing in this direction, which is really opposite to the assumed current of the capacitor, because usually in a capacitor we assume that the current flows from the positive plate to the negative plate. So you can write the expression again governing this one. This expression is that the voltage across the capacitor is equal to the voltage across the resistor, or Q over C plus IR is equal to 0. And here, if I move to the other side, of course, this takes into account the polarity. Okay, remember this one here will result in a positive, negative expression here. So I can simply replace the current by dq by dt, and then I can integrate both sides, integrate this term, the Q term relative to Q, and the RC term relative to T, as we did earlier. I am now integrating I will allow the capacitor discharge from time 0 to time t, so its charge will go down from Q naught to some Q. Of course, this one will give us again the len. You put upper limit minus lower limit. Len minus len gives you the len of the ratio. This one here will give you minus T over RC. Okay, then you can raise both sides to the exponential. Again, you get the expected result that the capacitor charge is really decreasing with time, and it's exponentially decreasing. So it starts with some initial charge Q naught, and then start to decay with time. If you want to, of course, I can divide both sides by C here, and then I get the expression for the voltage. The voltage at any time t is equal to the initial voltage multiplying by e to the minus T over RC. This one is exactly identical to this one by dividing both sides by C, and remembering that Q and V are related to each other by C. Now, the current going through the capacitor is simply dq by dt. So you differentiate this term here relative to T, so you get minus 1 over RC. Minus Q, this term here, Q naught over C is the initial voltage. So initial voltage over R will give you the initial current. And I put here a negative sign because remember, I naught is not flowing inside the capacitor, it's flowing from the capacitor. So the initial current is actually negative. I naught is actually negative here in this case. It's minus Q naught over RC. So this tells us the same result that we know, that the capacitor would start to discharge a very strong current, but gradually and slowly as it loses charge, the current will start to decay with time. And it's actually decaying in an exponential way. And after time t equal to tau, the current flowing in this circuit will have dropped to almost 1/3 of its initial value. Now let's take a look at an example of this, and I thought of giving you an example that helps you understand the charging and discharging cycles of a capacitor. So here we have a capacitor, it's a 10 nanofarad capacitor. It is discharging through these two resistors, 100K and 100K, and this switch keeps on moving every 1 millisecond from position 1 to position 2, and then back to position 1 again. So after 1 millisecond it will go from 1 to 2, after 2 milliseconds it goes from 2 to 1, after 3 milliseconds it goes from 1 to 2. So every 1 millisecond it keeps on changing position. So when it's in position 2, the capacitor is charging from the battery through the 100K, but when the capacitor goes to position 1, it is discharging through the 200K. So this is very important to understand, because the time constant tau of a charge is different from the time constant of this charge. So tau for charging is equal to RC, where R here is 100K and C is 10 nanofarad, while tau for discharging is equal to 200K multiplied by C. It's very important to understand the difference. So now let's see how we can find the capacitor voltage in every cycle. How is the capacitor charging and discharging? In the very beginning, we assumed that the capacitor was at position 1. It did not have any charge. So at time 0, the capacitor is position 1. There is no voltage across the capacitor. After 1 millisecond, the capacitor switched to position 2. So the capacitor will start charging. So this means it is charging from an initial voltage of 0. So the expression for the charging is the capacitor voltage equal to the battery voltage, which is 500 volts, multiplied by 1 e to the minus t over RC. And as I have explained to you earlier, it is charging through only one resistor of value 100K. So this one here is 100K, this one here is 10 nanofarad. So it will continue to charge for 1 complete millisecond until it switches back again to position number 1. So at the end of this 1 millisecond, which is really 2 milliseconds in the global time, what will be the voltage across the capacitor? You come back here and you put t equal to 1 millisecond. I want this to be very clear to you. The capacitor started to charge the 0, it was in position 1, and then at 1 millisecond went to position 2. It started to charge from 1 to 2. So here, this is the reference for charging. 0 is here and 1 is here. It was a charging up to here. So when we use this expression, we substitute for t equal to 1 millisecond, not 2 milliseconds, because it started charging at time t equal to 1 millisecond. Okay, so let's now calculate that voltage at the end of 1 millisecond. So when the capacitor was allowed to charge for 1 complete millisecond, so after 2 milliseconds of the start of our operation, this is the voltage across the capacitor. It's E, 1 e to the minus, this is the time, it's 1 millisecond, divided by 100K, so 10 to the power 5, multiplied by 10 to the minus 8, which is 10 nanofarad. This whole quantity will give you only minus 1. So the voltage at the end of 1 millisecond is 316 volts. Now the capacitor the switch will switch to position number 2. Then the capacitor will start to discharge starting from this voltage through the 200K resistors. Remember, now it's charging from this initial voltage through the 100K and another 100K. So now we have to write the expression for the discharging curve, and I'm going to be using the expression I'm asking you to drive. The expression that the capacitor is charging from a certain initial voltage. Actually, the expression we can use here is the one I've given you. This one actually it was Q equal to Q naught e to the minus t over RC, or that V is equal to V naught e to the minus t over RC. So when the switch switches to position number 2, the capacitor will start to discharge from its initial voltage of 316 volts. It is discharging through the 200K resistors, so the sum of the two resistors, and the capacitance here is 10 nanofarad or 10 to the minus 8. So remember, I'm allowing it to discharge only for 1 millisecond. So when I come back here, I will start and put the time to be 1 millisecond, not 3 milliseconds. Okay, because this curve assumes an initial voltage of 316. So at time 0 for this expression, the voltage was 316. It's a very important mistake not to make. Okay, so you put this one here, 316. Time is 1 millisecond. It's charging through 200K, so 2 to the power 5, and this one here is 10 nanofarads. So this whole thing will give you minus half. So at the end of this 3 milliseconds, the capacitor has a voltage, or at the end of this cycle, this charge cycle, the capacitor has a voltage of 192 volts. Okay, so first it was 0, it switched after 1 millisecond, it was charged for 2 milliseconds. Okay, and now this is charging. Actually, to be correct, this one here should be 3 milliseconds, because this is the end of the discharge cycle. Okay, this has to be 3 milliseconds. So now, because it was first 0 in position 1, and then switch it to position, so this position 1 there was 0, and then it was switch, it starts charging in position number 2 for another millisecond. So this is 1 millisecond, this will take us to another 2, and then it was discharging between 2 and 3 milliseconds, and now it will start to charge again. Okay, so now at exactly 3 milliseconds, the capacitor will switch back again to position number 2, where it is charging. But remember, it's not charging from 0, it's charging from 192 volts. Okay, so now it will continue to charge up to 4 milliseconds. Okay, so I made a mistake here in my all my calculations are correct, but remember, 0 into position 1 there was no charge. 1 millisecond switch, it switched to charge, start to charge here, and then discharge and discharge again. So now we move to the second charging cycle. It is charging up from 192 volts through only 100K. So now I will use the expression I asked you to derive, that V is equal to E plus V naught minus E to the minus T over RC. This is the expression for a capacitor charging through a battery of value of voltage E, but it has some initial voltage E naught and V naught, and this is what we have here, because we are starting to charge from 192 volts up to a battery voltage of 500 volts. Of course, we're not going to be charging the full battery voltage because the time is very limited, but remember, we are charging only through one resistor 100K, and the capacitor value is 10 nanofarad or 10 to the minus 8 farad. Now, if you calculate this expression, subtract 500 minus 192, this expression will give you 308. So this number is minus 308. So this is the expression really for the voltage charging. And remember, if you put here t equal to 1 millisecond, we calculated that before. For 1 millisecond, this number is equal to minus 1. And I'm not putting here 4 milliseconds, it's 1 millisecond. And here I have the same mistake. This here is really 4 milliseconds. This is the end of the 4 milliseconds. So, having done so, you can calculate the expression for the voltage at the end of 4 milliseconds. This is another charging cycle. We started by 192 volts. And if you make the calculation, you multiply this by E minus 1, you see that the capacitor up to you will see that the capacitor charged up to 387 volts. So after 3 milliseconds of the first switch to the position, to the charging position, the capacitor voltage went up from 0 in the very beginning to 387 volts. So it went actually through a number of cycles. I can try to do them for you here. 0, it was a position 1, so there was 0 volts this is 0 millisecond here. 1 millisecond start to charge up to certain value, okay, and then again at 2 milliseconds start to discharge, and make this one 2 milliseconds, and then at 3 milliseconds start to charge again. It went up higher, and then it will go start discharge again, and so on.